All right, so the sad thing is that I've recorded this video 3 times now, and at this point I'm trying to just get my audio on top of the video. So starting with sideways parabolas, I apologize, the video was recorded first. This is my third or fourth attempt at getting video. So starting with a basic parabola, y equals x squared. You know what that looks like. It starts decreasing, it ends up increasing. It is horizontal, meaning that there's a slope of 0 at the vertex. And then our sideways parabola is x equals y squared. Notice how your upright parabola opens up towards positive y values, while your sideways parabola is going to open right towards positive x values. Let's see. Let's watch. Is it always this painful to watch me draw stuff? Okay. So there's, oh, and look, I decided I didn't like my parabola. So the first time I recorded the video with audio, but it didn't pick up my audio. And the second time I recorded the audio, it didn't save my audio. And so we're trying again. Okay, so here I'm gonna emphasize that there's a, going for a different color, horizontal slope on your upright parabola, which means there's got to be a vertical slope on the sideways parabola. What we're going to be graphing more of, we are going to be graphing sideways parabolas I wish I could pause the video, in later on in the semester, but right now we're going to be graphing square root functions, which is half of a sideways parabola. So I solved for y by taking the square root of both sides. Remember, when you take the square root of both sides, you need the plus and minus. So you have your positive square root of x and your negative square root of x. And one is going to be, the positive square root of x will be the positive parts of or the non-negative parts, I should say, of your sideways parabola. And your negative square root x are going to be your non-positive parts of your sideways parabola. And again, when you draw these, you should go up and then out instead of just out. Okay, so up before you go out. You guys see how I'm slowly sketching them? I'm not trying to draw them in one fell swoop, because it's harder to maintain your shape when you're just, especially on here. Okay, a lot of you guys have a tendency to graph your sideways parabolas like that at the bottom. That's bad. Bad sideways parabola. It does not project proper slopes. And you know what I love? I love slope. Okay, so the bottom graph is not going to be acceptable. I think at this point, I throw stickers on there. I have to stay true to the slopes on these things. It's very, very, very important. And so I will be taking off points if your sideways parabolas are not reflecting the proper slope at the vertex of that sideways parabola. Okay. Good sideways parabola. Good square root function, and then bad square root function. Your square root functions need to go up and then out, not just out. Okay, so please pay attention when you're graphing them. Okie dokie. What's next? I talked a lot in this video. I apologize, guys. Did I do a shift? Oh, I was asking what would make it if I were to, domain and range. So domain of your square root function, which is going to be something that you're expected to graph. So the category on this should be square root function, not sideways parabolas. You can take square root of 0. Square root of 0 is just 0. A lot of students are like, I can't take the square root of 0. Yeah, you can. Square root of 0 is 0. And then you could take square roots of positive numbers. You just can't take square roots of negative numbers. So our domain is either from 0 to infinity, including 0, or x is greater than or equal to 0. Range is the same, except the alternative is y is greater than or equal to 0. Again, because you can't get negative values out of this thing. Okay, so this is the function. This is number 5 on our list of functions you guys need to know. Again, not the sideways parabola necessarily right now, but specifically the square root function. Okay, and then I think I was asking, so you're gonna need to be able to graph this basic shifts up, down, left, right. The things that I told you about trying to figure out which way it's been going, if it's gone left or right, are true for this function, same as the other ones. The question I think I was posing was, how do you make it in quadrant 2 instead of in quadrant 1? And you have to make it so now if you're in quadrant 2, your x values are negative, but they have to become positive, so we throw a negative in front and we get ourselves flipped over the y-axis. because if you throw a negative in front of a negative value, it becomes positive, and then you'll be able to take its square root. All right, and again, when you're graphing these square root functions, you're going up and then out, or if it's been flipped over the x-axis, then it would be down and out. Okay, I thought my next thing... what's the, semicircles. Okay, so let's start with a circle. What's the equation for a circle centered at the origin with radius r? And that equation is x squared plus y squared equals r squared. I'm feeling a lot of sympathy for you guys watching these torturous videos. So for example, x squared plus y squared equals 4 would be a circle centered at the origin with a radius 2, right? Because r squared. So if you're gonna draw that, I think I started before I drew my axes. And so here's something else about when you're graphing, even if you're given a grid, okay, normally your y and your x-axis would be labeled, but you still have to, you can't just assume that one little tick mark on the grid is equal to 1 unit. So even though I have tick marks, I still labeled what I'm considering 2 units, which is 4 little tick marks. And I did that specifically so that you could see my picture, because if I made, it would have just been a really tiny circle if I had just made each tick mark worth 1 unit. So there's my circle, x squared plus y squared equals 4. This is not a function, right? It fails the vertical line test. Okay, we can't talk about its domain and range. So what we're going to be talking about is the semicircle. So you're going to solve for y. So go ahead and pause my video, solve for y, and come back to me when you're ready. Solving for y means make it say y equals. Okay, so the first step is going to be able to bring the x squared to the other side. So we'll have y squared equals r squared minus x squared. And then I'm going to do the square root of both sides. But when you do the square root of both sides, don't forget your plus and minus there. Okay, so plus and minus the square root of r squared minus x squared. All right, and just like with your square root functions, you have one's the top half. They're 2 separate ones. You can't keep them together, otherwise you don't have a function. So you have the positive square root of r squared minus x squared, you have the negative square root of r squared minus x squared. One's the top half of the circle, the other one's the bottom half of the circle. Okay, the top half of the circle is our main focus for this part. You're not going to be doing shifts left, right, up, down. The big is going to be like a flip over the x-axis. The domain on this is weird. It's from negative r to r, right? Like think about the circle x squared plus y squared equals 4. If I looked at just the semicircle part of it, your domain, that would just give you the top part of it, right? And the domain would be from negative 2 to 2, which is indicative of your negative r to r. The range on this particular semicircle is from 0 to 2. So that's from 0 to r. So you know it looks weird with the r's there, but the range on this thing is going to go from 0 to 2. And so in general, the range on the square root of r squared minus x squared is from 0 to r, including both endpoints. Okay, again, not ups, downs, lefts or rights. We're going to be, but one thing that you do need to do is you need to recognize the formula for a semicircle, because if it shows up in an integral in January, you're going to need to be able to draw that semicircle. We can't do much with a semicircle. Here I gave you an example of like what you might be asked to graph is like, oh, it flipped over the x-axis, right? Nothing crazy, no lefts, no rights, no ups, no downs. Well, maybe ups and downs later on, or you can, it's avoidable. But again, to recognize anytime you see this equation that it's a semicircle, and to know that what that semicircle relates to graphically is very, very important. We talked about those interconnections that AP stresses. So when you guys are working with square root functions, you're going to have to be, just like with absolute value functions, you're going to have to be looking at them graphically. All right, what did I do next? The suspense is killing me. Oh, I was talking about slopes here. So the top part of a semicircle is horizontal, so is the bottom part of the circle is horizontal. That means the sides are vertical when you're graphing a semicircle. I should see that to the best of your ability. I know they're not going to be perfect, but I want you to try. All right, and again, I'm focusing on that's what the core of this slide is. That's number 6 on our list for our list of our 10 functions that you need to be able to graph quickly. And then hopefully I move on to the next slide. What's taking me so long? I talk too much. I repeat myself a lot. It's partly a good teacher tactic, but right now I wonder what I was saying. I don't know. In case it makes you feel any better, this has tortured me way more than it tortured you. You could put me on double speed, can't ya? Yeah. Or you could skip ahead right now. I can't skip ahead. I can't edit in this program. I need to, here we go, the new slide. Oh, and look at that adorable picture of Owen. Okay, so exponential functions, a lot of times we talk about exponential growth and exponential decay. The general format of these equations is a times b to the x. And the a is just a coefficient here. If b is greater than 1, we have exponential growth. Okay, if b is between 0 and 1, we are going to have exponential decay. So exponential growth is a lot about population growth, whether it be the population of deer in a forest or bacteria in a petri dish. Population of cities and states don't tend to actually grow exponentially, and we'll talk about that more in BC. But for right now, you guys have done a lot of exponential growth and exponential decay problems, both in your math and in your science classes. Decay with like carbon dating and that kind of stuff. And a lot of they all look pretty much the same. Okay, so I started comparing y equals 2 to the x, y equals 3 to the x, and y equals e to the x, just to give you some variety. Hopefully I write those things soon. I think I was going on and on about exponential growth and exponential decay. Sometimes I'm concise and sometimes I'm verbose. I apologize. I was being really lazy with not wanting to re-record all of the writing on here. It's just that it was annoying. But now this is also annoying. I apologize. I also procrastinated after my initial failures. I was like, I put it aside. I didn't come back to it. Oh my goodness, what am I talking about? Where are my functions? 2 to the x, 3 to the x, and e to the x. E is called Euler's number. It's just a special number, especially if you go into engineering, you're gonna see E a lot. This old dude, Leonhard Euler, and Euler's last name starts with an E, kept coming up with this number E. And so his followers named it after him. Here we go, 2 to the x, 3 to the x. And e to the x. So you guys know, so, you know, if you do 2 to a power, 3 to a power, nobody stresses. But when you guys do e to a power, you're like, oh my goodness, what's going on? It's the same thing. Okay, e is just Euler's number. It's around 2.7 something. So it's between 2 and 3. Okay, so if you were to compare these curves on the same graph, you would see there would just be a slight difference in steepness between them. And yes, that is pronounced Euler. It is not pronounced Euler. It does not rhyme with Ferris Bueller. Although if you haven't seen the movie Ferris Bueller's Day Off, you really need to watch that because it's kind of a cult classic. Okay. Okay, so E is around 2.7 something. I said that before. At some point I relate it to pi, where you know how 3.1415296 blah 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 kept showing up in ancient Greece, and so they gave it a symbol so they wouldn't have to keep writing that stupid number. It's not a stupid number. It's a beautiful number that goes on forever. They gave it a symbol. So the folks were like, this 2.7 something keeps showing up. It must be important. Let's call it something so we don't have to keep writing the stupid number. I'm sorry, the very long number. I shouldn't call things stupid. My daughter tells me that's a bad word. But yeah, so they gave it the number E, the letter E to represent it. In terms of graphing these, I think you guys know the basic shape of exponential growth, whether or not you think you do or not. Our anchor point is our y-intercept. If you plug in 0 to any of these things, like 2 to the 0 is 1, 3 to the 0 is 1, e to the 0 is 1. So, oh, you know, I started with plugging in 1 first, which was a mistake. So, okay. So if I'm going to graph y equals 2 to the x, if I do 2 to the 0, I get 1. If I do 2 to the first, I get 2. If I do 2 squared, I get 4. If I do 2 cubed, I get 8. If I do 2 to the fourth, I get 16. I'm not sure if I actually hit 16 on this one. These boxes are really small to count. Let's just pretend that that works. If I plug in -1, 2 to the -1 is the same as 1 over 2, right? And then if I do 2 to the -2, that's 1 over 2 squared, which is a quarter. Okay, so they're going to consistently get smaller as I go this way, which is very much the behavior of an asymptote. So I have a horizontal asymptote here that when my x's get smaller, I'm sorry, when my x's get more negative, my y values get closer and closer to 0. All right, I want to follow along with what I write. I feel like I should have just, okay, so my anchor point, hopefully I'm writing as the 0.01 on all of these. Right, that's my y-intercept. Okay, the only way you could change that is if you shift it up or down, or left or right, or if you have a coefficient out front, you could change your anchor point. Okay. Okay, so the y-intercept of 1 is common to our basic exponential functions regardless of the base. Okay, and then, you know, it's just the steepness on the next point. So 2 to the x has the 0.12, 3 to the x has the 0.13, e to the x has the 0.1e, okay, which is 2.7 something. Okay, so the graphs are going to look very similar in terms of all three of these guys. I don't know if you guys heard DJ. She just said kiss kiss. Oh, and now she's squawking. When I graph these, I'm super lazy about it. I put my axes, I do my swoosh, I label my y-intercept. Thank you, Gigi. Okay. Her name is DJ. Sometimes we call her Gigi because it stands for grumpy girl because you hear her squawking like that. All right, I want to address this horizontal asymptote thing. Okay. The domain on exponential functions is all real numbers because there's no restriction on what you can put into an exponent. As far as the range goes, and you could see it from the graph, like I can get huge positive numbers, I can get small positive numbers, I can never get to 0. And if you disagree with that, try to plug in a number and get to 0. Like 2 to what power can give you 0? If I do something like 2 to the -10th, okay, I'm gonna get 1 over 2 to the 10th, which is a very tiny, tiny number, but it's still not 0. What if I did 2 to the -100th? That would be 1 over 2 to the 100th. That's a minuscule number, okay? But it's still not 0. So my range is going to be, we don't need that anymore, is going to be y is greater than 0 or from 0 to infinity, excluding the endpoint. That behavior, when you have that on the left side of this graph on the x-axis, is called a horizontal asymptote. There is a teacher in the building who calls them horizontal asymptotes. Please, that's not how it's spelled. Horizontal asymptotes with a T at the end. Okay, and the whole idea of the horizontal asymptote, and you don't have to draw it with a little dashy line if it's on the x-axis, or if you had a vertical if it was on the y-axis. But if it moves with an up-down shift, then you have to draw it with the little dashy line. So please don't forget that part. It's easy to see the little dashy line here because I have 3 colors going, but if you didn't have 3 colors going, then it would be nearly impossible for you guys to see it. Okay, so graphing y equals e to the x plus 1, I want to talk about how I would graph that. The plus 1 at the end is a shift up 1 unit. So you're gonna shift your horizontal asymptote up 1 unit. So you draw it in with your little dashy line and you label it. Oh, I don't know why I circled that. Oh, so horizontal asymptote is normal, y equals 0. It relates to the range. That's probably what I was talking about. Okay, the whole idea of a horizontal asymptote, and there it is. So I bumped it up 1, I labeled it. So I drew my little dashy line, I labeled it. Okay, my anchor point also is going up 1. So now it's at 0, 2. I'm gonna label that too. If I don't label it, oh good, good. I was gonna say I better label it. All right, and then I draw my graph. I'm fixing the end a little bit. I love how the eraser tool, like, things fall off the bottom. Isn't that great? In any case, if for those of you guys that have an older sibling, like my brother used to stick his finger in my face all the time and get really, really close to my face and go, I'm not touching you, I'm not touching you, I'm not touching you. And he would get closer and closer and closer. That's what your graphs do with your asymptotes. They do the I'm not touching you game, and they just get closer and closer and closer and closer and closer without ever touching. Okay. All right. I would think I would be on the next slide by now. You'd think. What's taking so long? Little tweets. Oh, I'm highlighting. Okay, so never touching the asymptote, getting infinitely closer, but never touching. I don't know what I was babbling about. I apologize, guys. Logarithms! Everybody hates logarithms, so I put a silly picture of Owen looking terrified. The biggest thing for you guys to remember about logarithms is that exponential functions and logarithmic functions are inverses. Okay, so logs are inverses of exponentials. When you guys find an inverse, if you guys think back to Algebra 2, when you first found inverses, the very first step to finding an inverse is just switching x's and y's. So that's what we're going to be thinking about. Natural log is best. So we love y equals natural log x. And the common log, we're kind of done with. Okay, so we're going to see it. Common log is meh, I said. It's log base 10. And it's not... it's just not functional, right? With the calculator, it can only do natural log and common log, but a lot of times you don't want common log, you don't want log base 10. Natural log kind of takes care of all of it. I know you guys saw all these conversion formulas. That was because we didn't used to have the technology that we do. Okay, so I don't really want to see common logs too much. We are going to be taking their derivatives and their antiderivatives that we're going to see a formula and move on with it. But for the most part, when we're working with logs, it's going to be the natural log. Okay, so going back to the fact that these are they're inverses of each other. For y equals e to the x, we said in the last slide that the domain was all reals and the range was from 0 to infinity exclusive. We had an anchor point, okay, and that point was the point 0, 1. And my horizontal asymptote was y equals 0. Yes. Okay, I had a moment, I think, when I was like, I just said it too, and I was like, is it y equals 0 or x? It's y equals 0, the horizontal asymptote. Okay, so now for your natural log, because these are inverses, everything is literally going to swap. Okay, so x's become y's, y's become x's, domains become ranges, ranges become domains, inputs become outputs, right? Because to find an inverse, you swap the x and the y's. That's literally the very first step in finding an inverse function back from Algebra 2. Okay. So for y equals natural log x, the domain from e to the x of all real numbers is going to become the range of natural log x. So the range of natural log has to be all real numbers. Okay, my domain from e to the x, those are my outputs, have to become my inputs for natural log. Okay, so I'm going to go from 0 to infinity. except now we're talking about x values instead of y values. So for a domain from 0 to infinity, let me draw some axes on this grid. Oh, the anchor point before I do that. Okay, so the anchor point, swapping x's and y's instead of 0, 1, it's going to be 1, 0. If I swap x's and y's and I had an equation of an asymptote of y equals 0, it becomes x equals 0, which is no longer a horizontal asymptote. It's now a vertical asymptote. Okay, so understanding the relationship between these two things, a lot of you guys just hate log graphs and you're like, oh, I don't know how to do them. You do know how to do them, okay? So with this domain of from 0 to infinity, that means that I'm in only quadrants 1 and 4, right? That's saying x is greater than 0. So my graph can only be contained in quadrants 1 and 4, which I'm just gonna highlight here. And then just in terms of clues, because a lot of you guys are like, you just put up this mental block in terms of your log functions and you're like, I don't know how to graph them, I don't know how to graph them, but you can use the clues from before and figure out how to graph them. All right, the range is all real numbers. So that means both quadrants 1 and 4 are good to go. Okay, so I can draw both of those. My anchor point is 1, 0. Hopefully I'll throw that on shortly. There we go. Oh, and then I'm like, oh no, it's too fat. I'm gonna go get another marker. See? There we go. Okay, and you guys see how it's 2 tick marks out because I wanted it big enough, but I'm labeling it so that you know that that's the point 1, 0. Okay, my vertical asymptote is gonna be there. You don't have to draw it in because it's on the x-axis. You guys can see it's really hard to see because it's in the same color. It's even worse on your paper. I'm not sure what I was about to write. So something to understand about logs is that it's getting to the exponent. So if we go with y equals 2 to the x and swap our x's and y's to find an inverse and make it x equals 2 to the y, x is the answer now and y is the exponent. So when you turn this into a log expression, which would be log base 2 of x, okay, it's important for you to understand that x is still the answer and y is still the exponent. Okay, so when you're talking about logs, you're talking about what are the exponents, all right? And so when you're figuring out how to draw this, if I want my y's are my exponents. So if my exponents are bigger, my answers are gonna be bigger. In order to get bigger answers, I'm gonna need bigger exponents. So that's gonna get you, to get bigger answers, meaning bigger x values, you need bigger exponents, meaning bigger y values. So the graph is gonna look like that up there, okay? And then if I look between 0 and 1, so now if I take answers, if I want answers that are between 0 and 1, so fractional answers, I need negative exponents. So that's why you're gonna swoop towards that play that I'm not touching you game with the vertical asymptote here. Okay, so this is what our log function looks like. Okay, I showed you guys an example of if I do negative the natural log of x, what that's gonna do. Okay, it's just gonna flip me over. It's gonna make all my negative y values positive and all my positive y values negative. So, oh, I didn't label the y-intercept. I'm sorry, the x-intercept. I should have labeled the x-intercept of 1 there. Okay, that's an incomplete graph. Moving on to y equals natural log of x plus 1. How come sometimes it's so slow and sometimes it's so fast? This is the same thing that we did with our parabolas and our cubics. Like, what's happening here? Well, if I do x plus 1, that interior, ask yourself, where is that 0? When I'm taking natural log of 0 is undefined. So that's going to be where my asymptote is. So what number do I have to plug in for x? -1. If I plug in -1, I have natural log of 0. That's where I'm undefined. So that's where my asymptote is. And then I screw up this graph. My I totally messed this up. Everything got moved left one. So instead of having the 0.10, it should have been the 0.00. This graph should be going through the origin right now, not the 0.01. I apologize for that, guys. And I will show you guys the proper picture of in like a separate something. I don't know, because I totally messed that one up. Okay, so some things to know. Natural log of 0 is undefined. Okay, you could either write UND or DNE. Natural log, because natural log of 0 is saying e to what power is 0, and there is no. And then natural log of 1 is 0 because e to the 0 is 1. See how that works? We have some log rules that we're going to use throughout the semester, but not super a ton, but let's just get them out. So natural log of a product, it's natural log of A plus the natural log of B. Natural log of a quotient is equal to the natural log of A minus the natural log of B. And the natural log of A to the B, that's the third one. You can drop down the B, and it's B times the natural log of A. Okay, so those are the things that we need to know about our natural log graphs. Again, my last graph. Oh, and we're at the very last slide. Thank goodness. There's only 6 minutes left. I'm very happy to say that to you. And I don't know what happened because these were fine when I started with but they got moved. So hang on for 1 second. So the last two functions are y equals 1 over x and y equals 1 over x squared. They are rational functions. I remember being in high school and being like, what is a rational function? Why does my teacher keep talking about rational functions? Rational functions, think about a ratio as just a fraction. So rational functions are just fraction functions. Okay, so y equals 1 over x and y equals 1 over x squared, that's supposed to say. I fix it at some point so that you could read it better. So they're rational functions, meaning that they have fractions in them. Ratio means fraction. Well, it's a proportion, which is a fraction. Okay, as far as our domains and our ranges go on these, remember when you have fraction functions, denominators can't be 0. Okay, so for both of these, my domain is just that x can't be 0, okay, because I can't have a 0 in my denominator. As far as my ranges go, think about the types of values you can get out of this function. I can get positives, I can get big positives, I can get small positives, I can get negatives, I can get big negatives, I can get small negatives. I just can't get 0. I can't do 1 divided by a number and get 0. So our range is y can't be 0. Okay, for y equals 1 over x squared, it's similar, okay, except that because I'm squaring everything, I can only get positives. I can get big positives, I can get small positives. I just can't get any zeros or negatives out of this. Okay, that looks a little more like 1 over x squared now. So for this one, my range is y is greater than 0. Okay. Home stretch, guys. We got 4 minutes left for this video. Horizontal asymptotes and vertical asymptotes come into play on both of these. They both have both at same y equals 0, x equals 0. Okay, the values that you can't get out, you're gonna play the I'm not touching you game with. So you can't get out zeros, so you're gonna approach 0 infinitely closer, or approach huge numbers, and we'll talk about this more in person, I think. Okay, so 1 over x, if I plug in numbers, if I plug in 1, I get 1. If I plug in 2, I get a half. If I plug in 3, I get a third. If I plug in 4, I get a quarter. So I see that this way I'm getting closer and closer and closer to the x-axis. My values are getting closer to 0. Okay, if I plug in something like a half to 1 over x, I'm doing 1 divided by a half, which is 1 times 2, which is 2. Okay, and then if I do 1 divided by a quarter, I'm gonna get 4. If I do 1 divided by a tenth, I'm gonna get 10. All right, so these numbers are gonna explode up here. And we're gonna have a vertical asymptote that we're gonna play the I'm not touching you game with. Okay, and then you're gonna have similar stuff when x is negative, except all your y values are gonna be negative. So you're gonna have essentially the same thing, but in quadrant 3 instead of in quadrant 1. Okay, x's and y's both negative. And my pictures are not perfect, but they're accurate. Okay. The graph for y equals 1 over x squared is very similar. Okay, so the right side is still in quadrant 1. When x is positive, y is positive. Okay, and the steepness on this should be a little bit different, but again, we don't really care about being precise. We just need it to be accurate. And then when x is negative, because I'm squaring those values, everything is positive. So instead of having it in quadrant 3, it's going to be in quadrant 2. Okay, for these, it's going to be up, down, left, right shifts. I'm going to do 1 or 2 examples for you guys. When you shift up, down, left, right, I expect those asymptotes to also shift up, down, left, right. So please do so accordingly. All right, so y equals 1 over x minus 1 is a down 1 shift. So I'm dropping my horizontal asymptote down 1. And then I'm just going to draw my above on the right side and my below on the left side. And I'm going to call it a day. You should label. I don't know if my label got just hard to see because it's so tiny. But you should definitely label that asymptote is at -1. All right, and then I think I went a little crazy. So I have y equals 1 over x plus 1 quantity squared. And because I'm changing the x value before the function part of it, right, so the 1 over x was 1 over x, and then I did -1. Here I'm doing x plus 1, and then I'm squaring it and flipping it. Okay, taking its reciprocal 1 over. So that's a left-right shift. And again, if you're not sure what it is, ask yourself, where is the 0? So it's 0 when x is -1. Our domain is another way to think about it. X can't be -1. That's going to be where our vertical asymptote is. So I'm going to draw it, and I labeled this time, which is good. Okay. Oh, and then I think I was like, hey, let's shift it up to 2. Also. Up to also. So just so you could see. So I'm shifting up to, hopefully I label. Yeah, I label 2. And then everything is above the horizontal asymptote. So we're going to draw it in there. Okay. And those are our graphs that we need to know. All right. I hope you guys have a good rest of the weekend.